Good morning everyone, myself Muskan. I am from B.Sc Chemistry Honors 3rd year. My roll number is 54. Today I am going to read a chapter of Organic Chemistry of Pradeep's written by Dr. S.N. Dhwan. Chapter Organosulphur Compounds. Introduction. Sulfur is placed in the third period of the periodic table just below oxygen in group 16. During the recent past, a lot of work has been carried out in the area of organosulfur compounds, primarily due to their importance in industry, pharmaceuticals and metabolic processes. Therefore, in this unit we shall discuss such some important aspects of the chemistry of organosulfur compounds. Structural feature. Both oxygen and sulfur alter the chemical nature of carbon atom to which they are attached. But unlike oxygen analogues, in most of sulfur compounds, the reaction occurs by the attack of a nucleophile, an electrophile, or even a free radical at the sulfur atom. Another marked difference between oxygen and sulfur compound is that unlike oxygen, which readily forms double bond, sulfur is reluctant to form double bond by pp overlapping. Thus, with the exception of carbon disulfide CS2, thiocarbon compound R2C double bond S are quite unstable and readily undergo addition reactions. In other words, thioaldehydes and most of the thioketones can be generated only as transient intermediates that rapidly undergo dimerization, trimerization, and polymerization to form compound having only single sigma bond. For example, a thiocarbonyl dimer, a thiocarbonyl trimer. The instability of the thiocarbonyl compound is primarily due to the difference in the size of the 2p orbital of carbon and 3p orbital of sulfur, which makes 2p 3p overlapping relatively ineffective. In addition of poor 2p 3p overlapping, sulfur is also reluctant to form 3p 3p pi bond with other sulfur atom. It is because of the reason that elemental sulfur does not exist as diatomic S2 unlike O2 molecule. Instead, it prefers to form only SS sigma bonds and exist as a non-planar octa-atomic molecule S8 having crown shape. Further, due to the larger size of sulfur atoms, SS bond is quite long. As a result, the two 3p orbitals, one on each S atom, can't come close enough to undergo 3p 3p overlap to a significant extent, and hence the pi bond between 3p 3p orbital is very weak. In it may, however, be noted that unlike thioaldehyde and thioketones, thioamide and thioacids are isolable and hence are relatively stable. This contradicts the generalization that pi bond involving sulfur atom are very weak. The actual reason for the stability in the is the resonance stabilization involving lone pairs of electron on nitrogen or oxygen atom. Thioamides, thioacids. Here the contribution of structure 2 towards resonance hybrid of thioamides and that of structure 4 towards resonance hybrid of thioacid is significant because both of them have only single bond between C and S atoms. We have discussed above that sulfur has little tendency to form pi bond through pp overlap. However, many sulfur compounds such as dimethyl sulfoxide DMSO, a widely used aprotic solvent, have pi bond between sulfur and oxygen atom. As anticipated, this double bond, like any other double bond, consists of a sigma bond and a pi bond. The sigma bond is formed by heat on overlap between sp3 orbital of sulfur and one of the half-filled p orbital, say 2px of oxygen. The other two sp3 orbital of S overlap with sp3 orbitals of 2 alkyl group to form two additional sigma bond, while the fourth sp3 orbital consists a lone pair of electrons, sulfur is now left with a half-filled d orbital, and oxygen also has an half-filled p orbital. Since dxy lies in the plane of 2py orbital and dzx lies in the plane of 2pz orbital. Therefore, d pi overlap occurs either between dxy and 2py orbital to form a pi bond. In valence bond terms, this d pi bonding implies that DMSO may be regarded as a resonance hybrid of the following contributing structures. Since DMSO has a high dipole moment 3.9 d, this suggests that structure 1 makes a significant contribution towards the resonance hybrid, which of course is much greater than that of structure 3. An important difference between ordinary double bond with p pi overlap and sulfur oxygen double bond with p pi d pi overlap is that the group attached to sulfur do not lie in the plane. This explains why acetone is planar while DMSO is non-planar. Structure of thiols and thioethers. Both in thiols and thioether, S is sp3 hybridized in the ground state and not in the excited state as shown. Such a sp3 hybridized sulfur has two half-filled orbitals which overlap with a sp3 orbital of an alkyl group and a s sulfur of the H atom as in thiols, or with sp3 orbitals of two alkyl groups as in thioethers. Each of the remaining two sp3 orbitals contain a pair of electrons. However, due to greater lone pair repulsion than bond pair repulsion, the CSH bond angle decreases from 109 to 28 minutes to 100 in CH3SH. In contrast, in thioethers, due to greater steric hindrance between two alkyl group than between an alkyl group and a hydrogen atom in thiols, the bond angle in thioethers is larger than in thiols. For example, methyl thioether has a bond angle of 105 . Structure of sulfonic acid. In sulfonic acid, RSO3H or ArSO3H. S is also sp3 hybridized, since here we need to form two sulfur oxygen double bond. Therefore, both the 3s and 3p electron are promoted to d orbital as shown below. The 4sp3 orbital of sulfur form 4 sigma bond, one with the carbon atom of the alkyl or the aryl group and 3 with the oxygen atom. S is now left with two unhybridized d orbital which overlap with p orbital of two oxygen atom to form 2 d pi p pi s double bond O bond. The p orbital of the third oxygen atom overlap with s orbital of hydrogen to form an OH bond. The sulfonic acid have tetrahedral structure. S attaches CH3H and two lone pair sp3 orbitals. For the purpose of nomenclature, sulfur compounds are classified according to the valence state of sulfur. The compound containing bivalent sulfur are structurally analogous to the corresponding oxygen compounds such as alcohols, carbonyl compound, carboxylic acid, etc. Therefore, they are often named by adding the prefix thio to the name of the corresponding oxygen analogy. For example, thioalcohol, thiophenol, diethyl thioether, thiourea, thioacetone, dithioacetic acid, thioacetaldehyde. For naming the compound having sulfur is placed in place of carbon, the prefix thio is sometimes used. Thiocyclohexane 2,5-diethyl-1,6-hexahexane diol. For compound having sulfur in the higher oxidation state, special names are used. Methane sulfonic acid, benzene sulfonic acid, para-toluene sulfonyl chloride, dimethyl sulfone, etc. Thiols or thioalcohols. Just as alcohol are alkyl derivative of H2O, in the same way, thioalcohol are alkyl derivative of H2S. HOH, water में से H रिमूव करेंगे, R add ROH form. Thus, the general formula of thiol alcohol is RSH. In the IPEX system, thiol alcohol are called thiols. They are also called mercaptans. Mercurium is equals to mercury, captans is equals to catching. Since they react with mercury, two ion form insoluble mercury compound RS2Hg. The functional group of thiol alcohol is SH. It is called sulfide thiol or mercepto. A number of sulfur compounds are found in nature. For example, butane thiol is found in skunk, an American animal. Propane thiol occur is onion. Allyl merceptan and allyl disulfide occur in garlic. Nomenclature of thiol. These are named according to the following systems. Number one, common names. In the common system, thiol alcohol are called merceptans. The individual name of any thiol alcohol is then derived by adding the word merceptan to the name of the alkyl group. Number two, IPEX system. In the IPEX system, thiol alcohol are called thiols. The individual name of any thiol alcohol is in then obtained by adding the suffix thiol to the name of the hydrocarbon containing the same number of carbon atom. In case of isomeric thiol, the position of SH group is indicated by the lowest possible Arabic numeral. In case of polyfunctional compound, the thiol is named as the mercepto derivation of the principal functional group. It may be noted that OH group is assigned higher priority both in numbering and naming. For example, कॉमन नेम बीटा हाइड्रोक्सी इथाइल मर्सेप्टेन आईपैक नेम है 2 मर्सेप्टो इथेनॉल. कॉमन नेम एम मर्सेप्टो बेंजोइक एसिड और आईपैक नेम 3 मर्सेप्टो बेंजोइक एसिड. 3.5 Methods of formation. Thiol alcohol are generally prepared by the following methods. Number 1. From alkyl halide. When alkyl halide are heated with a large excess of sodium or potassium hydrosulfide, thiols are formed. Sodium hydroxide plus Rx in presence of heat form alkene thiol plus Na positive X negative. Potassium hydrogen sulfide plus CH3CH2I in presence of heat, the formation of ethane thiol. From number 2, from sodium alkyl sulfate or para-toluene sulfonic esters. When sodium alkyl sulfate is heated with sodium hydrogen sulfide, thiol is formed. Sodium methyl sulfate plus Na positive SH negative. In presence of heat, methane thiol is formed plus Na2SO4. Ethyl paratoluene sulfonate plus NaSH in presence of heat. Ethane thiol plus sodium paratoluene sulfonate is formed. Number 3, from alcohol. Merceptans are prepared from alcohol either by treating with phosphorus pentasulfide or by passing a mixture of hydrogen sulfide and alcohol vapor over thoria catalyst at 673 Kelvin. For example, ethanol plus P2S5 in presence of heat, ethane thiol plus P2O5 is formed. Number 4, from alkenes. Addition of hydrogen sulfide to the carbon-carbon double bond of an alkene in presence of nickel sulfide as catalyst leads to the formation of thiols. Alkene plus HSH form 2-alkene thiol. The addition occur in accordance with Markovnikov's rule. Terminal thiol can however be prepared by free radical addition of H2S to an alkene. Alkene plus HSH in presence of anti-Markovnikov's rule, in presence of light, form 1-alkene thiol. Number 5, from thiourea or S-alkyl isothiuronium salt. When alkyl bromide or iodide are treated with thiourea, S-alkyl isothiurium salt are produced. These upon alkaline hydrolysis gives thiol in about 80 to 90% yield. Thiourea in presence of RBr form S-alkyl isothiurium bromide. then hydrolysis, on which hydrolysis form urea. This is the best method for preparing thiol. Number 6, from Grignard reagent. The reaction of Grignard reagent with sulfur powder gives addition product which upon hydrolysis gives thiol. Grignard reagent plus S. Formation of additional product which on hydrolysis give alkene thiol plus MgOHx. 3.6, physical properties. Number 1, physical state, smell, etc. Methane thiol is a gas while other thiol are colorless, volatile liquid with disagreeable smells. The lower member have extremely strong smell while higher member have mild odor. The odor of freshly cut onions is due to propane 1 thiol and that of garlic is partly due to prop 2 in 1 thiol CH2 double bond CH single bond CH2 single bond SH. Small quantities of ethane thiol are added to LPG to warn against leakage of the gas. Number 2, boiling point. Due to absence of hydrogen atom, the boiling point of lower thiol alcohol have lower than those of the corresponding alcohol. However, thiol having 8 or more carbon atoms have slightly higher boiling point than corresponding alcohol due to stronger van der Waals forces of attraction and weaker H bonds. Number 3, solubility. Thiols are less soluble in water than the corresponding alcohols. This is due to the reason that thiol can't form H bonds with water. Number 4, dipole moment. Due to small electronegativity of S than O, SH bond is less polar than OH bond. As a result, Thai alcohol have lower dipole moment than other corresponding alcohols. 3.7, chemical reactions. The thiols resemble alcohol in many ways. The main difference in their behavior is towards oxidizing agents. Some important chemical reaction of diols are discussed below. Number 1, acidic nature. Thai alcohol are stronger acidic than alcohol. This is because of following two reasons. Number 1, the bond dissociation energy of SH bond 347.3 kilojoule is much lower than that of OH bond 464.4 kilojoule. As a result, SH bond is cleaved more easily than the OH bond. Number 2, the anion left after the removal of a proton from RSH, that is RS negative, has a negative charge on S atom, while in case of alcohol, that is RO negative, it is an oxygen atom. Because of the larger size of sulfur, RS negative can accommodate the negative charge more easily than the smaller oxygen atom in RO negative ion. Some important reaction of thiols due to their acidic nature are discussed below. Number 1, reaction with alkalis. Due to their stronger acidic nature, they dissolve in NaOH or KOH, forming their corresponding salts called merceptides. The reaction is reversible and merceptides are completely hydrolyzed by water in absence of alkali. RSH plus NaOH form RSNA positive plus H2O. Number 2, reaction with mercury oxide. Being acidic, thiols react with mercuric oxide to form mercury merceptide. Number 3, reaction of alkaline metal. Alkali metal. Alkali metal being strong base react with merceptans to form the corresponding merceptides with evolution of H2 gas. Number 4, action of heavy metal salt. When a thiol is treated with the aqueous solution of the salt of the heavy metal, example lead acetate, a merceptide is obtained. These heavy metal merceptide are generally covalent compound. Number 2, reaction of carboxylic acid. Thiol react with carboxylic acid, preferably in presence of an inorganic acid as catalyst to form the corresponding thioesters. Acid plus thiol in presence of H positive give thioester plus H2O. The equilibrium lies mainly to the left. However, a good yield of an ester is obtained if acid chloride is used instead of acid. Number 3, oxidation. Due to weaker SH bond, thiols can be easily oxidized. The nature of the product, however, depend upon the nature of the oxidizing agent used. With mild oxidizing agents such as air, H2O2, CuCl2, or sodium hypochlorite and AOCl, thiol are oxidized to dialkyl sulfides RSH plus H2O2 give dialkyl disulfide plus 2H2O. An alkaline solution of sodium plumbite containing sulfur doctor solution also convert thiols to dialkyl disulfide. Dialkyl disulfides can also be prepared by the action of iodine on sodium merceptides. With strong oxidizing agents such as HNO3, periodic acid, etc., thiols are converted into sulfonic acid. Thiol plus 3O in presence of HNO3 give alkane sulfonic acid. This gives us an important point of difference between thiol and alcohol in their behavior towards oxidation. Whereas in alcohol, oxidation increases the oxidation state of carbon, while in case of thiol, the oxidation state of sulfur increase. Number 4, reduction. Reduction. On treatment with Raney nickel, thiol readily undergo desulfurization to form the corresponding hydrocarbon RSH in presence of Raney nickel form RH plus NiS. Number 5, action of aldehyde and ketone. Thiols readily combine with aldehyde and ketones in presence of hydrochloric acid to form merceptols and merceptols respectively. For example, acetaldehyde plus ethane thiol in presence of HCl give diethyl methyl merceptals plus H2O. When these merceptals and merceptols in ethanol are refluxed in the presence of nickel, the thiol group is replaced by hydrogen. Thus, merceptal and merceptol formation in acidic medium followed by disulfurization with Raney nickel gives us an excellent method for conversion of a carbonyl group to methylene group under neutral conditions. This method is, however, competitive with Clemson reduction, which is carried out under acidic conditions, and Wolff-Kishner reduction, which is carried out under basic conditions. Therefore, like acetals and ketols, merceptals and merceptols can also be used for protection of the aldehyde ketone group in acidic medium. Oxidation of merceptols. Merceptols are easily oxidized to sulfanols. For example, oxidation of acetone merceptol with KMNO4 gives sulfonal. Acetone merceptol in presence of KMNO4 give sulfonal. Sulfonal is used as an hypnotic, that is sleep-inducing drug. Homologues of sulfonal, namely trional and tetragonal, are even more effective hypnotics. Trional or tetragonal. Thioethers. Thioethers may be regarded either as dialkyl derivative of H2S or alkyl derivative of thioalcohols. They may also be regarded as derivatives of ether in which oxygen has been replaced of sulfur. Diethyl ether, oxygen is replaced by sulfur, give diethyl thioethers. 3.8 Nomenclature. The common name of thioethers are obtained by adding the word sulfonide or thioethers to the name of the alkyl group arranged in alphabetical order. In the IPEC system, thioethers are named as alkyl thioalkanes. The sulfur atom is taken with the smaller alkyl group which form a part of the alkyl thio group, while the larger alkyl group forms a part of the alkane. The common with parentheses and IPEC name of some thioether are given. CH3SCH3, methyl thiomethane. Next, methyl thioethane, ethyl thioethane, 3-methyl thiocyclohex 1-one. 3.9 Method of formation. By heating potassium sulfide with an alkyl halide alkyl sulfate or potassium tosylate. Potassium sulfide plus alkyl halide give thioether plus Kx. The yield are generally good to fairly good. Number 2, by heating an ether with potassium pentasulfide. Ether plus potassium pentasulfide in presence of heat give thioether plus P2O5. The yield are often poor. Number 3, by heating an alkyl halide with a sodium merceptide. This method is used sodium methyl merceptile plus 3CH3I. Follow SN2 give ethyl methyl sulfide. This method is similar to Williamson synthesis and can be used for the synthesis of both symmetrical and as unsymmetrical thioethers. Since alkyl sulfide is a better nucleophile than alkoxide ion, the reaction is very rapid and gives excellent yields. By addition of a thiol to an alkene in presence of peroxide in presence of heat give R dash plus 2 CO2. By passing a thiol over a mixture of number 5 by passing a thiol over a mixture of heated alumina and zinc sulfide at 573 Kelvin. Thiol give thioether plus H2S. 3.10 Physical properties. Number 1 Physical state. Thioethers are colorless, oily liquid having unpleasant smell. Number 2 Solubility. They have insoluble in water but soluble in organic solvents such as alcohol, ether, etc. Number 3 Boiling point. In general, their boiling point are relatively higher than those of corresponding ether. This is due to stronger van der Waals forces of attraction in thioether are compared to ethers, primarily due to bigger size of sulfur than oxygen atom. 3.11 Chemical reactions. Although ethers are relatively unreactive, thioether are quite reactive. Their reactivity is primarily due to the ability of the divalent sulfur atom to get converted into compound with plus 4 and plus 6 oxidation state. The main difference lies in the formation of sulfoxide and sulfones on oxidation and to form sulfonium salt with alkyl halide. Some of their important chemical reactions are described below. Number 1 Weak basic character. Due to presence of lone pair of electron on the s atom, thioethers like ethers behave as weak bases. As such, they dissolve in 100% H2SO4 to form sulfonium salt. Number 2 Reaction with alkyl halide. Being sufficiently nucleophilic, thioether react with alkyl halide by SN2 mechanism to form trialkyl sulfonium salt. It may be noted that here the tertiary amine of the type R1, R2, R3N could not be resolved in spite of the fact that they also tetrahedral structure. The reason cited was that the energy difference between the two enantiomer was quite low, and thus rapid interconversions between the two enantiomer gave a racemic mixture. However, in case of sulfonium salt, the energy difference between the two enantiomer is sufficiently high and hence can't be readily interconverted. Therefore, sulfonium salt can be easily dissolved. These sulfonium salt are stable at room temperature but decompose on heating to alkyl sulfide and alkyl halide. With moist silver oxide, these sulfonium salt form sulfonium hydroxide, which are strong bases. These sulfonium hydroxide decompose on heating to form the original alkyl sulfide and an alkene. This reaction may occur either by E2 or even mechanisms depending upon the nature of the alkyl groups. If all the groups are 1 degree, the reaction occurs by E2 mechanisms. If, however, one of the group is 3 degree, the reaction occurs by E1 mechanisms. Number 3 Formation of sulfur yield and their reactions. The sulfonium salt on treatment with a strong base such as N-butyl lithium eliminate an alpha hydrogen to form dialkyl sulfonium methylide, commonly known as sulfur yield. These sulfur yield are extremely useful synthetic reagent and have been widely used for the synthesis of epoxides and cyclopropane derivative by reacting them with a ketone or an activated olefin. Number 4 Oxidation. Thioethers and on oxidation first give sulfoxide and then sulfones. Number 1 with mild oxidizing agent. With mild oxidizing agent like HiO4 at 273 Kelvin, oxidation can be stopped at the sulfoxide stage. For example, dimethyl sulfide in presence of HiO4 give dimethyl sulfoxide. Number 2 with moderate and strong oxidizing agent. With moderate oxidizing agent such as H2O2 in glacial acetic acid, diethyl sulfide give first diethyl sulfoxide and then diethyl sulfone. However, with strong oxidizing agents such as KMNO4, HNO3, etc., sulfones are directly obtained. Number 5, reduction. Alkyl sulfide on treatment with Raney nickel readily undergo reduction and desulfurization, forming alkanes. Number 6, reaction with bromine. Alkyl sulfide form many addition products. For example, addition of bromine gives diaryl sulfide dibromide. Undergo reduction and desulfurization, forming alkanes. Number 6, reaction with bromine. Alkyl sulfide reaction with bromine. Alkyl sulfide form many addition products. For example, addition of bromine give dialkyl sulfide dibromide. Sulfonic acid. Sulfonic acid are organic compound having the general formula RSO3H, where R may be an alkyl or aryl group. The alphabetic sulfonic acid are named either as alkyl sulfonic acid or as alkane sulfonic acid, while aromatic sulfonic acid are named only as arene sulfonic acid. For example, methyl sulfonic acid or methane sulfonic acid, etc. 3.12 Method of formation. Aliphatic sulfonic acid. Aliphatic sulfonic acid are generally prepared by the following methods. Number 1, oxidation of thiol. Thiol on oxidation with HNO3, KMNO4, NaOBr, etc. Undergo oxidation coupling since SH bonds are much weaker than OH bond to form first dialkyl disulfide, which under the condition of the reaction are further oxidized to alkyl sulfonic acid via thiosulfonate esters and disulfone, or through sulfinic and sulfinic acid as shown below. Number 2, sulfonation of alkane. Sulfonation of alkane with concentrate H2SO4, oleum or chlorosulfonic acid give alkane sulfonic acid. The sulfonic acid group generally enters the chain at second carbon atom. N-hexane plus SO3 give hexane to sulfonic acid. Number 3, action of sulphiryl chloride on alkenes. The action of sulphiryl chloride or a mixture of Cl2 and SO2 or an alkene in presence of light or peroxide at 313 to 323 Kelvin gives the corresponding alkane sulfonyl chloride in high yield. Here again the SO2Cl group enters mainly at the second position of the chain through a varying amount of product with this group at the first carbon are also formed. Number 4, Stracker reaction. Sodium salt of sulfonic acid are obtained when an alkyl halide is heated with sodium sulfite. Number 5, addition of sodium bisulfite to alkenes. In presence of oxygen or peroxide, anti-Markovnikov's addition of sodium bisulfite to alkenes gives the sodium salt of corresponding alkene sulfonic acid. 3.12 Aromatic sulfonic acids. Aromatic sulfonic acid are produced by sulfonation of aromatic hydrocarbon with concentrated H2SO4, fuming sulfuric acid, sulfur trioxide, and 1-protopyridium sulfonate C5H5N plus SO3. The choice of the sulfonating agent and the condition employed mainly depend upon the type of aromatic compound to be sulfonated. When the aromatic compound contain an activating group, the sulfonation is usually carried out with concentrated H2SO4 at relatively low temperature. In contrast, sulfonation of deactivated aromatic compound is carried out with fuming H2SO4 at high temperature. 1-protopyridium sulfonate is mainly used for sulfonation of acid-sensitive aromatic compounds such as furan, pyrrole, etc. 3.13 Physical properties. Number 1, aliphatic sulfonic acid are colorless liquid or low melting solid, while aromatic sulfonic acid are colorless crystalline solid which are highly hygroscopic in nature. Number 2, the melting point of sulfonic acid are lower than the corresponding carboxylic acid. This is because the absence of hydrogen atom in sulfonic acid, as a result of which they exist as discrete molecule, while aliphatic carboxylic acid exists as cyclic dimers due to hydrogen bonding. 3.14 Chemical reactions. Some important chemical reactions of sulfonic acid are discussed below. Number 1, acidic nature. Sulfonic acid are completely ionized in aqueous solution. They are as strong acid as H2SO4. Sulfonetine is a resonance hybrid of the following three equivalent resonating structures. As a result, negative charge is dispersed on all the three oxygen atom and hence sulfonic acid are strong acid. In contrast, the carboxylate ion is stabilized by two equivalent resonating structure. Therefore, carboxylic acid are weaker acid than sulfonic acid. Being acidic, sulfonic acid neutralized, alkalize, and decompose carbonates and bicarbonate evolving CO2 gas. Number 2, formation of acid chloride. When treated with thionyl chloride or phosphorus pentachloride, they form the corresponding sulfonyl chlorides. These sulfonyl chloride on treatment with ammonium or alcohol in presence of alkali form the corresponding sulfonamide and sulfonic ester respectively. Alkyl sulfonyl chloride plus 2NH3 give alkyl sulfonamide plus NH4Cl. Number 3, formation of anhydrides. On heating with phosphorus pentaoxide, sulfonic acid form the corresponding anhydride. Sulfonic acid gives sulfonic acid anhydride plus H2O in presence of P2O5. Replacement reaction of arene sulfonic acids. A number of reagents can bring about the replacement of sulfonic acid group by other group. This is because sulfonic acid is an excellent leaving group. This property makes sulfonic acid as valuable reagent in organic synthesis. A few important reactions of this type discussed. Number 1, replacement by OH group. Hence sodium benzene sulfonate is fused with alkali. Sodium phenoxide is produced. Sodium benzene sulfonate plus 2 NaOH gives sodium phenoxide. Number 2, replacement by NH2 group. When sodium arene sulfonate are fused with sodamide, primary aromatic amine are formed. Sodium arene sulfonate plus NaNH2 gives 1 degree amine plus Na2SO3. Number 3, replacement by CN group. When fused with NaCN, sodium salt of arene sulfonic acid give aryl cyanide. Number 4, replacement by SH group. Sodium arene sulfonate on fusion with sodium hydrosulfide give thiophenols. Number 5, replacement by H desulfonation. Sulfonation follows the principle of microscopic reversibility. Thus, when arene sulfonic acid are heated with dilute HCl under pressure at 423 to 473 Kelvin, arenes are produced. The mechanism of desulfonation is just reverse of sulfonation. Number 6, replacement by a halogen atom or a nitro group. When a sulfonic acid group is located at ortho or para position with respect to the OH or the NH2 group, it is knocked off and replaced by NO2 group or X atom during nitration and halogenation respectively. 3.15 sulfonamides. Sulfonamide are derivative of sulfonic acid in which OH part of the sulfonic acid group has been replaced by NH2 group or the substituted amino group such as NHR or NR2. For example, sulfonamide and methylbenzene sulfonamide. 3.151 preparation. Sulfonamide are generally prepared by the action of ammonia primary or secondary amine on the corresponding sulfonyl chloride. For example, benzene sulfonide chloride plus 2 NH3 give benzene sulfonamide plus NH4Cl. Properties. Sulfonamide, number 1, sulfonamide are well defined crystalline solid and are therefore used to characterize sulfonic acid. Number 2, acidic nature. They are weakly acidic in nature and hence react with strong alkalis to form water soluble salt. Number 3, hydrolysis. Sulfonamide on heating with aqueous acid or alkalis under hydrolysis to form the corresponding sulfonic acids. Uses. They are used in the manufacture. Number 1, dyes. Number 2, antiseptics such as chloramine T. And number 2, 3, sulfa drugs. Sulfa guanide synthesis, acetanilide or chlorosulfonation with excess of chlorosulfonic acid give para-acetamidobenzene sulfonyl chloride, which upon treatment with guanidine followed by acid hydrolysis give sulfaguanidine. That is itself prepared by heating cyanamide with ammonium chloride. Uses. Sulfa Guanidine is an important sulfur drug and is used for treatment of bacillary dysentery since it is only slight absorbed in the intestinal tract. Therefore, it is given in relatively large doses. Synthetic detergent. These days, in place of soaps, the substance which are being largely used as cleansing agent as synthetic detergent, as the name suggests, they are obtained from purely synthetic chemical as compared to soaps which are derived from chemical obtained from natural sources like oils, fat, etc. In fact, synthetic detergent are sodium or potassium salt of long chain alkyl hydrogen sulfates or aryl sulfonic acid. Unlike soap, synthetic detergent can also be conveniently used even in hard water. This is due to the reason that calcium and magnesium salt of detergent like their salt, sodium or potassium salt are also soluble in water. Hence, synthetic detergent do not form curdy white precipitate with hard water. Further, they can also be used in acidic solution. However, synthetic detergent have one disadvantage. Unlike soaps, they are not completely biodegradable and hence cause water pollution. The typical synthetic detergent are either alkyl sulfates or alkyl benzene sulfonates. A. Sodium alkyl sulfates. They are obtained from long chain alcohol by treatment with concentric H2SO4 followed by neutralization with NaOH. Some important examples of this type of detergent are sodium lauryl sulfate and sodium stearyl sulfate. Sodium lauryl sulfate is also commonly known as sodium dodecyl sulfate SDS. It is mainly used in shampoos and cosmetics. This sodium alkyl sulfates is 100% biodegradable. These are also effective in slightly acidic solutions since they form an alkyl hydrogen sulfate which is soluble material, whereas soap react with acidic solution to form insoluble fatty acids. B. Alkyl benzene sulfonates. The most commonly used domestic detergent these days are linear alkyl benzene sulfonate LAS, such as sodium P benzene sulfonate. They are anionic detergent and are obtained by conversion of benzene into long chain alkyl benzene followed by sulfonation and neutralization with NaOH. Another important example is sodium P2-decyl benzene sulfonate. It is prepared by Friedel-Crafts alkylation of benzene with a long chain alkyl halide or an alkene or an alcohol followed by sulfonation and neutralization with NaOH. Alkyl benzene sulfonate, in which the phenyl group is either attached to the end of long alkyl chain or any other secondary position, have high biodegradability and hence are called soft detergents, while alkyl benzene sulfonate having branched chain alkyl group have poor biodegradability and hence are called hard detergent. Cleansing action of soaps and detergents. All the soaps and detergent contain two characteristic group, that is a water soluble hydrophilic group and an oil soluble lyophilic or lipophilic group. As a result, one end of the molecule of a soap or detergent tends to go into oil phase and other end tends to go into water phase, with the net result that the material soap or detergent concentrate at the surface of solution or interface. The dirt is generally held to a dirty surface by a thin film or of an oil or grease. When the dirty surface is treated with soap solution, the non-polar hydrocarbon chain of the soap or detergent. This lowers the surface tension between water and grease. As a result, a stable emulsion of oil in water is formed when the surface or the cloth is mechanically scrubbed. The loosened dirt particles are absorbed by colloidal soap or detergent particles are ultimately washed away. Thank you.